This lecture is based on the book Practical Approximate Analysis of Beams and Frames, and it summarizes some basic ideas presented in Chapter 1 from Section 1 to 4 out of 14 sections. This lecture and the book also assume that you know about free body diagrams, about shear and moment diagrams, and equilibrium equations. In this lecture, I will introduce two simple reference cases and a generalization of those cases. I will explain two core concepts and show how to use those to step-by-step approximately analyze a simple example. By analyze, I mean sketch the deformed shape with the approximate location of all inflection points, and sketch the bending moment diagram with approximate value for all the internal moments at key points. We start with one of the simplest configuration, a simply supported beam. This means there are hinges at both ends and we apply a moment at one end. This straw shows the deformed shape. This shape would be about the same for a steel, concrete, or wood beam, but of course with much smaller deformations. Those deformations are usually so small that they cannot be discerned visually without magnification or without sensitive cameras. To apply the bending moment, I'm actually applying two forces that are separated by a short distance. The two forces are not equal, and my thumb is applying a force up more than my index finger is applying a force down. So there is a net force up and a net applied moment. The net force up simulates the effect of the left hinge. On the other side, I apply a single force down sufficient to keep the beam horizontal. This force down would be provided by the hinge on the right side. By applying a moment, we get a specific shape that has more curvature on the left side. The angle on the left is larger than that of the right. Finally, the maximum displacement is not at the center, but occurs closer to the side where the moment is applied. If we compare the theoretical deformation with the deformation of the straw, we get a good match. Now, we consider how to sketch this case by hand. We start by drawing stubs or small line extensions at each side. We choose an arbitrary but exaggeratedly large slope for the stub on the left end. We do this so that the shape is clear. On the right side, the angle appears to be smaller. Theoretically, for this case, it is half of the other end. So, on the right side, we draw a stub at a slope about half the other end. We extend this stub on the right and we want to meet with this line from the other side tangentially. We want to have the maximum height to occur at about 42% of the length from the left end, which is the theoretically exact location. Well, we locate the middle and move a little bit to the left. No need to be too precise in a sketch. And we mark the maximum level with a line at about that distance. The height of the maximum is theoretically about 45% of the height of the extended line on the left. So, about half. Now, we draw a rough arc curving downwards, and that is tangent to the stub at the left end, and meets the maximum height line at about the marked location. Finally, we remove or erase the extraneous lines, smooth out our curve to get our deformed shape. Some or all of these steps may be omitted once we get a sufficient familiarity with sketching this shape, but this step-by-step approach makes us aware of all the salient details of the beam or column's deformation. And now we compare with the theoretical shape. This theoretical shape matches the deformed straw, and yes, we again get a good match, this time between theory and sketch. Before moving on, we need a little terminology and a sign convention. In particular, we want to talk about curvature. Curvature is approximately the slope of the slope, or the second derivative of the displacement curve. As a convention, we will consider a decreasing slope to be negative curvature. It looks like a frown or a half frown. A constant slope, or a straight line, has of course zero curvature. Finally, an increasing slope will be referred to as positive curvature. It looks like a smile or a half smile. Negative curvature has a decreasing slope, which either means that the slope is becoming less positive or less going up, and it can also mean that the slope is becoming more negative or more going down. Similarly, positive curvature has an increasing slope, which either means that the slope is becoming less negative or less going down, and it can also mean that the slope is becoming more positive or more going up. Why should we be concerned with curvature at all? In beams and columns, bending moments are linearly related to the curvature, and bending stresses, which is the main thing in designing beams, is linearly related to the bending moments. This means that visually, Seeing curvature is seeing relative bending stresses. Yes, curvature is how we actually see relative bending stresses. So it's worth it to have more refinement in recognizing curvatures and their relative amplitudes across the beam or column. We can almost feel the bending stress building if we animate a small beam with equal and opposite moments applied at each end. This also shows why many use this particular convention of positive and negative curvature. However, be warned, this convention is not universal. Now, let's go back to the beam and look at some quantitative results. Looking at the deformed shape, we find that the angle where the moment is applied is twice the angle at the other end. The maximum displacement occurs at about 42% from where the moment is applied. This turns out to be the farthest distance from the applied moment that you can move the location of the maximum displacement by applying a moment at one end and connecting any kind of passive structure at the other end. Next, we note that there is a relation between the applied moment m and the resulting rotation theta. The moment m equals 3ei over L times the rotation theta, where E is Young's modulus, I is the moment of inertia, and L is the length of the member. This is a linear relation between the applied moment and the rotation, and we can think of the beam as a rotational or helical spring at the left support with a rotary stiffness of 3ei over L. The moment diagram for this basic case is quite simple. It is a straight line starting at a value of negative the applied moment and ending at 0 at the free hinge side. That zero moment, which also means zero curvature, is why we extended a straight line from that end when sketching the moment diagram. The next simple configuration is a beam with a moment applied at one end and a fixed support at the other. This straw can again demonstrate the deformed shape. This shape would be about the same as for a steel, concrete, or wood beam, but of course, again, with much smaller deformations. We could use a digital camera and software to calculate optical flow to capture this deformation in real beams. Again, we apply the bending moment in the same way as before. This time we feel that to make the same rotation as in the simply supported case, we need to push a little more with our fingers. Theoretically, we need a third more effort. By comparison, we would have to put twice as much effort if the straw was half as long. On the other side, I now need to also apply a moment like on the other side, and again with a net force down so that my index finger will be applying more force than my thumb. I need to apply enough net force to make this side level with the other and to apply enough moment so that the tangent to the straw at this end is horizontal. The shape that we now get is different from the simply supported or hinge-hinge case. This shape has both negative and positive curvature. At some point between negative and positive, this curvature, and therefore also the bending moment, must be zero, and we call that point the inflection point. An inflection point is where the bending moment, curvature, and bending stresses are all zero. It is the eye of the bending stress storm. Now, we again compare the theoretical deformation with the deformation of the straw, and again we get a good match. Let's now sketch this case by hand. We again start by drawing stubs or small line extensions at each side. We choose an arbitrary but large slope for the stub on the left end so that the shape is clear. On the right side we draw a small horizontal stub. We want to have the maximum height to occur at about a third the length from the left end, which is the theoretically exact location. Well, we locate that approximately and we mark the maximum level with a line at about that distance. Again, it turns out that the maximum should theoretically be at about 45% of the height of the extended line on the left. And we draw a small line at that height. Now, as before, we draw a rough arc curving downwards, starting tangent to the stub at the left end. We try to have the maximum height tangent to our horizontal height guide. For the right end, we draw a parabola that starts horizontal, is tangent to the right stub, and meets the left arc tangentially at one point. Next, we smoothly join the two curves. We now remove or erase the extraneous lines to get our deformed shape. Finally, we mark the location of the inflection point by x, which is theoretically at exactly a third the length from the fixed support. Again, some or all of these steps may be omitted once we get a sufficient familiarity with sketching. But this step-by-step approach makes us aware of the salient details of the beam or column's deformation. And again, we compare with the theoretical shape, and yes, we again get a good match between theory and sketch. Now, for some quantitative results about this case. If we look for the inflection point, we find that it is at exactly a third the length from the fixed end. The maximum displacement occurs at exactly 1/3 from the other end, the end where the moment is applied. By contrast with the simply supported case, this turns out to be the nearest distance that the maximum displacement can be from the support by applying a moment at one end and connecting any kind of passive structure at the other end. Next, we note the relation between the applied moment and the resulting rotation. The moment m equals 4ei/L times the rotation theta, where E is Young's modulus, I is the moment of inertia, and L is the length of the member. The corresponding rotational or helical spring stiffness is 4ei/L. It is just 1/3 more than that of the simply supported beam. Not a large change considering the support at the left went from being free to rotate to being completely fixed. The moment diagram for this basic case is also simple. It is a straight line starting at a value of negative the applied moment, 0 at the inflection point, and half the applied moment, but positive at the fixed end. The moment at the fixed end is the carryover factor for moments that is used in Hardy-Cross or moment distribution method. The next configuration is a beam with a moment applied at one end, and the other end is neither fixed nor free to rotate freely, but somewhere in between. This is how it deforms. At the resisting end, I start with a simply supported configuration. That is, I just apply a finger down on the right side and gradually apply a resisting moment, but not enough to make it tangent to the horizontal. If we look at a beam connected to a structure and apply a moment at one end, we see that at the other side, that side is behaving as neither fixed nor free to rotate, but somewhere in between, just like the straw I demonstrated. At the node circled in yellow, where the loaded beam is connected to the rest of the structure, we see a transmitted moment trying to rotate that joint and is being resisted by the other members. Notice two things. The curvatures at the ends are consistent with how the transmitted and resisting moments are acting, and at the same time consistent with how the overall members are deforming. The second thing is that the angles at the connection remain 90 degrees, which is the way they initially started, but now the whole joint rotates as one unit. To model the situation of neither free nor fixed, we consider a beam AB connected to 3 other members, 2 of them columns. The bottom column is fixed at the base, the top column is connected to other unspecified members, and the beam has its other end connected to a free hinge. Each of the connected members acts like a rotary spring so that their combined effect is the sum of their rotational stiffness. We already know the rotational stiffness of 2 cases, and it doesn't matter if it's a beam or column as long as there is no difference in the transverse movement between the ends. In structural mechanics, we say that there is no side sway in any of the members. Member BD, the beam on the right, has a free hinge at D, and therefore it has a stiffness of 3ei/L, with EI and L, the length, being those of beam BD. Column BE, the bottom column, has a fixed end at its base, and so has a stiffness of 4ei/L, with EI and L, the length, being those of column BE. Finally, column BC is connected to other members, so its stiffness is somewhere between 3 and 4ei/L, with EI and L, the length, being those of column BC. The members connected to column BC at C also act like rotary springs. If we call the rotary stiffness 4k EI/L, again, EI/L are those of BC, then the stiffness is 4 times 3 plus 4k divided by 4 plus 4k. The little table shows some typical values for that adjustment, which goes from 3, corresponding to a freely rotating hinge, to 4, which corresponds to a fixed end. Here's where the main approximation comes in. Remember, the book and lecture is about approximate methods. We choose the stiffness of column BC to be 4ei/L, as if it had its top end fixed. A better approximation would be to use 3.6ei/L, because in the small table, we notice that the typical value between 3 and 4 is usually near 3.6. But that is more cumbersome, and the improvement in accuracy is not worth it. Now we have to add the rotational stiffnesses of the connected members and somehow normalize them, which means divide them by some reference to get a non-dimensional factor. So we define a rotary stiffness factor K, as opposed to a rotary stiffness, as the rotational stiffness of connected members divided by the hinge fixed case of the rotational stiffness of the member itself. The main approximation we will make is to use 4EI over L for all members that are not clearly freely hinged at their other side. What are typical values of K, the stiffness factor? For a continuous equal span beam, K is about 1. If a beam is connected to one same span beam and one column, then it is about 2. And if there is a beam and 2 columns, then it is about 3. 1, 2, 3. This is the ballpark values of K, the stiffness factor. And it turns out the results do not depend strongly on K as long as K is greater than 1. So now we see the deformation of a hinge rotational spring beam. Notice that, typically, it's closer to the freely rotating hinge case than it is to the fixed end case. There's a slight positive curvature visible near the spring, which becomes very clear only at unusually large stiffness factors that are not typically encountered. Now, we compare the deformation of a straw with this case, and we get a match. Okay, let us sketch the deformation for this case. We again start with stubs or small line extensions at each side. We choose a rather large slope for the stub on the left to get a clear shape. On the right side, the stub must have an angle that is usually less than a quarter of the other side. It does not seem that way with the straw nor with the figures of the theoretical results, because the curvature goes below the tangent on the left but above the tangent on the right. We want to have the maximum height to occur at between 1/3 and 42% of the length from the left hand, which is the theoretical range for its location. Well, we locate that at somewhere around 40%, and we mark the maximum level with a line at about that distance. Again, it turns out that the maximum should theoretically be at about 45% of the height of the extended line on the left, and we draw a small line at that height. Next, we draw a rough arc curving downwards and starts tangent to the stub at the left end. We try to have the maximum height tangent to our horizontal guide at about 40% of the length of the beam from the left end. For the right end, we draw a parabola that is tangent to the stub and tangent to the arc on the left so that we get a smooth transition. Next, we smoothly join the two curves, smooth things out, and remove extraneous lines. Finally, we mark the location of the inflection point by X at somewhere between 1/5 to 1/3 the length away from the support having the spring. We now have our deformed shape. Again, some or all of these steps may be omitted once we get sufficient familiarity with sketching, but the step-by-step approach makes us aware of all the salient details of the beam or column's deformation. We understand it better. Now, we again compare the theoretical deformation with the theoretical shape, and again we get a good match between theory and sketch. Having seen how to sketch this case, we will consider some quantitative results about it. If we look for the inflection point, we find that the distance of the inflection point from the spring support is given by a simple enough formula, which is 2k over 3 plus 6k times the length of the beam. If we look at the table of values, the inflection point coincides with the right support for the zero stiffness spring, which is a hinge or simply supported beam. It is at about 22% the length for an equal span continuous beam resting on external hinges, which has K approximately 1. It is at about 27% for an equal span continuous beam rigidly connected to columns, which has K approximately 2. It is at about 29% for an equal span beam that is part of a multi-story building, which has K approximately 3. And it is at exactly 1/3 for an infinitely stiff spring, which is a fixed end. So, for stiffness factors of 0, 1, 2, 3, and infinity, we have 0, 22, 27, 29, and 33%, which is a slow variation with K when K is above 1. For example, the distance of the inflection point from the support increases by only about 32% after tripling the stiffness factor from 1 to 3, and still only changes by 14% when we increase the stiffness factor from 3 to infinity. The moment diagram is also simple. It is a straight line starting at a value of negative the applied moment, 0 at the inflection point, and extending to a value that can be calculated using similar triangles at the right end. Alternatively, You can calculate the bending moment at the right end using an effective carryover factor, 2k over 3 plus 4k. If we look at the table of values, the carryover factor is 0 for a simply supported beam. It is about 29% for an equal span continuous beam resting on external hinges which has k approximately 1. It is about 36% for an equal span continuous beam rigidly connected to columns which has k approximately 2. It is 40% for an equal span beam that is part of a multi-story building which has k approximately 3. And it is 50% for an infinitely stiff spring which is a fixed end. So, for stiffness factors 0, 1, 2, 3, and infinity, we have 0, 29, 36, 40, and 50%, which is a slow variation with k when k is above 1. For example, the carryover factor increases by only about 38% after tripling the stiffness factor from 1 to 3, and still only changes by 25% when we increase the stiffness factor from 3 to infinity. If we look at the deformation and bending moment diagrams for varying values of the rotary stiffness factor, we can visually notice rapid change in values when the stiffness factor varies between 0 and 1, followed by a rather slow change afterwards. This is important because it suggests that if our basic approach in approximate analysis is to estimate the stiffness factors, then we expect good results because calculated values are not too sensitive on the rotary stiffness factor. We only need to be careful to distinguish between zero stiffness and non-zero stiffness at a connection. Before moving to an example of approximately analyzing a structure, we need one more ingredient. When we apply an external moment at a node or joint, the joint rotates, and at the same time it is resisted by the connected members. That disturbance causes deformation throughout the structure. We want to focus on the node where the moment is applied. That node is connected to 3 members, and we're looking very close, infinitesimally close, to the node. The node rotates and all 3 members resist the applied moment. But how much does each member resist? We basically have 3 rotational springs in parallel resisting the same moment. The solution is basic but worth quickly outlining. We start with moment equilibrium. We note that the rotation of all members are the same. We also note that the members respond as rotary springs. This allows us to substitute in the moment equilibrium equation, which we then solve for theta. Knowing theta, the rotation, we can get the individual moments by applying the spring relation for each member. The term that multiplies the applied moment to give us the individual bending moment in a member is the distribution factor. In general, the distribution factor for a member is the rotational spring stiffness of the member divided by the sum of the rotational spring stiffnesses of all the members together, including the member itself. If a connected member has its other end a free hinge, or alternatively a fixed end, then we know exactly its rotary stiffness. We looked at those cases before. If a connected member is connected to other members, then we use another approximation. We assume the spring stiffness to be approximately 4 EI over L, which is the stiffness if the other end is fixed. Based on previous discussions, a value of 3.6 EI over L would give slightly better results, but we will ignore this and just use the simpler estimate. Now, let's consider a moment applied at the end of a beam and its other end is attached to multiple members. The beam deforms as the moment is applied, and notice the curvature flip sign at the other end of the beam. This means that if the applied moment is counterclockwise at the starting node as shown, then it will be clockwise at the node on the other side of the beam. Let's isolate the beam and look at this again. The counterclockwise moment will lead to a clockwise transmitted moment. Also, if we want, we can estimate the value of this transmitted moment using the rotary stiffness factor idea with the approximate carryover factor 2k over 3 plus 4k. The transmitted moment acts just like an externally applied moment, and we can distribute its effect on the connected member in the same way. Each of those bending moments will transmit bending moments to their other side, which will either be a support or some other node where the new transmitted moments need to be distributed. Now we consider an example of a beam resting on supports and on one column as shown in the figure. We are also given values for EI and length of all beams and columns. Note that these are normalized dimensionless values which are much simpler and convenient to use. In particular, bending moments only depend on relative stiffnesses, so that using dimensionless values gives the same results. In this case, starting from dimensional values, we would divide all values of EI by the EI of the column and divide all member length by 1/3 the length of the column to obtain the values shown on the figure. We also have an applied moment of 100, dimensionless, and the ends of all members are labeled with letters for easy reference. We start by sketching the deformed shape of this structure. We will draw this over the original structure. We now isolate the member where the moment is applied. It is connected to two other members. We replace those two members by an equivalent rotary spring whose stiffness is the EI over L of beam BC plus EI over L of the column, divided by EI over L of the member AB itself. We now sketch the deformed shape that we've discussed, making sure to mark the location of the inflection point. We choose a rather large rotation at A so that the deformation of the rest of the members are sufficiently clear. Also notice that the connection or joint at B rotates as a unit, maintaining the original angles. Next, we calculate the location of the inflection point using the known formula or using the tables, and we mark this under the figure for easy reference. The exact location of the inflection point is at 1.25 from B, while we got a value of about 1.31. This is about 5% error, which is quite tolerable. Next, we can do either BC or column BE. In sketching those, we have to match the slopes to be consistent with the deformation of beam AB. Let's do beam BC first. We have a distributed moment at B. We will describe how to get MBC in details later. And at the other end, beam BC is attached to another beam. We replace the connected beam by a spring and calculate the spring factor. It is exactly equal to 1 because the two beams have the same EI and the same length. We draw the stubs. The one at B should be there already, and the stub at C should have a slope equals to 1/4. We don't have to be so precise, we just draw a slope that is less than half of the slope at B. Now we sketch the deformed shape of this member and mark the approximate location of the inflection point. Next, we calculate the location of that inflection point using the known formula, or using the tables, or simply by memory, but we must remember to multiply by the length of the member, which is 5. In this case, we get the exact location of the inflection point because we know the exact stiffness factor for this case. Namely, the stiffness factor is exactly 1. We now go back to column BE. This is a basic case, that of the hinge fixed beam, but the picture is rotated by 90 degrees. We sketch it and mark the location of the inflection point, which is exactly at 1/3 of the length from the fixed end. Last, we sketch beam CD, which is again the basic hinge fixed beam. We sketch it and mark the location of the inflection point, which is exactly at 1/3 of the length from the fixed end. Putting all the members together, we get a sketch of the whole structure, including the quantitative location of all inflection points. Next, let's sketch the bending moment diagram. We will draw it on a separate reference figure under the deformed shape. We extend lines from all the nodes or joints and also from all the inflection points. This is useful because the bending moments must be 0 at all inflection point locations, and we can mark those values right away. We start with a loaded member, which is beam AB. It has an applied moment at joint A and there are no other attached members. This means that the moment will all be taken by beam AB at joint A, and looking at the negative curvature in the deformed figure near A, we then have a negative moment equals to the applied moment. We mark it on the figure. At end B of member AB, we have a transmitted moment. We already calculated the stiffness factor at B, which had K approximately equal to 1.83. We either use a formula, tables, or similar triangles using the location of the inflection point to calculate the transmitted moment at B. If you use the tables, don't forget to multiply by the value of MAB, which equals 100. Doing this, we get the bending moment value at B on member AB, and this has an error of about 2% as compared to the exact result. The transmitted moment at B, which equals about 35.5, needs to be distributed to beam BC and column BE. We distribute moment MBA by using distribution factors. Notice that the lengths and EI values of the attached members are different. We get a moment of 19.4 for MBC with about 9% error overestimated, and 16.1 for MBE with about 5% error underestimated. We could have expected this because we are overestimating the rotary stiffness of the beam, but we are using the exact rotary stiffness of the column. To improve this, we could have used a typical reduction factor of 0.9 to get much lower errors, but the effort is not worth it. In practice, final results will be obtained using software, and these approximate methods are mostly used in preliminary design in getting more insight and in having an expectation for the values of the computer output in case we make some input or interpretation errors. So now we have the bending moments at the joint of B. We sketch the bending moment lines from beam BC and beam BE, which should pass through the inflection points. The moment at the other end of beam BC, MCB, is transmitted from MBC. We already calculated the stiffness factor at C for member BC, which had K equal to 1. We either use a formula, tables, or similar triangles, using the location of the inflection point, to calculate the transmitted moment at C. If you use tables, don't forget to multiply by the value of MBC, which equals 19.4. Doing this, we get the bending moment value at C approximately equal 5.5. Notice that this is already much smaller than the applied moment of 100 and can easily be neglected in preliminary design because the other loads would probably govern. The bending moment at the fixed support at E is half that at the other end. This gives a bending moment of 8 at the support. The last beam, beam CD, has a moment at C equal to that of beam BC at C, because there are no other attached members. Also, the moment at C is transmitted to D with a factor of half because D has a fixed support. And this completes the moment diagram, and we already have the deflected shape.